Hi, class. Okay, so I'd like to spend today reconstructing an AVL binary search tree. So the initials AVL are they come from the first letters of the last names of the individuals who created the algorithm. But the concept of a binary search tree is a broader idea. This is just one implementation. So there are, whenever we consider these data structures that will house the data in some manner which is either optimal to read from or optimal to write to, um, it it kind of has to be that thing from the beginning. So earlier in the semester, whenever we were doing proofs by induction, um, we and then recursion as well. Whenever we spoke of recursion, we have this thing which this property which holds at first, and then we modify it in some atomic way, and then it continues to be that thing because the way that we modified it made it just so, right? So that's like as vague as possible, right? But the idea of creating a tree at all, right? So you have just a dot, a single node, and that's a tree. It's a rooted tree. And if you grow it in just the right manner, so that every time you add a node, you add it so that the entire thing is still a tree, then the property holds. Um, so for binary search trees and heaps and anything else that we might discuss or that you might encounter later on in a data structures course, um, the concept is similar but stricter. So for a binary search tree, you want a balanced tree. So this is an example of an unbalanced tree. We can imagine the root to be here. Um, and so we can see what we would need to do in order to make this thing balanced. Um, so we would move the one up here, and then everything would be either on this level or on this level. But this level would be completely filled out, just like valence electrons, right? So you have to fill out the inner orbitals, and then you grow that. And then the next level would be partly populated. Uh, but for binary search trees, we want the additional property that the middle element is always right here. So the special thing about AVL trees is that they provide that guarantee, the guarantee that the middle element is there, with the additional benefit that they are balanced, so that the amount of time it takes to find any one item in your data structure is log n. So it's just as fast as binary search itself, where you're either right where you need to be, or you need to go left, or you need to go right. But because it's stored in a tree, the height is the logarithm of the total number of elements stored. So the binary search tree version of this, or the AVL version of this, is so 3 is in the middle. We just know that. And then everything, the everything to the left of 3 must be less than the value of whatever we're using to compare. In this case, we're just using the node's ID, its serial number. So both 1 and 2 need to be to the left of this. And there's 2 ways to represent that. Either 1 and then 2 to the right. So 1 is to the left of 3 because it's less than 3. 2 is to the right of 1 because it's greater than 1. So we could do it that way, or we could do it this way, where 2 is less than 3 and 1 is less than 2. Right? So So the less than and greater than property applies to all descendants of a particular node. So everything that is to the left of this value has that guarantee of being less than, or perhaps less than or equal to whatever was up here. So for the right hand side, we can do it like that, or where again 5 is greater than 3, so it's a right child, and then 4 is less than 5, so it's a left child. Okay, so we're going to create a structure in JavaScript that maintains these properties even as we add new elements to the tree, so that if you create a data structure, if you create new binary search tree or whatever, then each time you add an element to the tree, it preserves both the ordering and the balanced nature as it grows, so that whenever you look for something within the tree, you get it in logarithmic response time. Okay. So let's get started on that. Okay, so we're creating a graph or a node, right? Sorry, we're creating a graph or a tree, in this case a tree. So we need a create node function, something that will return new instances of the node. Or, I apologize, I should say we need the concept of a node or a vertex, since we are creating a tree. And of course, if we were creating a graph, we would need that as well. And so in JavaScript, it's very informal. Whenever you create a new object, just a pair of braces, and you get a new JavaScript object. But we've also referred to them in this course as hash tables, maps, dictionaries, and key value lookups. Okay, so these are all of the properties that you would expect a tree to have. So an individual node will have its height with respect to the tree, and then there's the value, which is the comparison value we're going to use. Parentage, right? So you should be able to traverse your way up the tree. This isn't strictly necessary if you only need to go down the tree. But if you want to be able to navigate the tree, which we are going to need to do, you need to hold a reference to the parent, and then, of course, a left and right child, which are null if you're dealing with the leaf node. And because we have this parent reference, there are two ways to resolve the parent of a root node. My preferred way to do it is to leave it as null. So if the parent is null, then you have root. That way you have this easy criteria to test in. And if you're going up the tree inside of a loop or a recursive function, you have some easy halting criteria. If the node is null, or if parent is null, then return. But you can also set parent you can also set root's parent to itself, so that parent is equal to this for that particular instance. And that's valid. I just don't think it's and it's beneficial whenever you're dealing with operating systems and you have the tree structure. When you're dealing with file systems and you have the tree structure of the file system, the parent directory of root is always itself. And so I think in that case it makes sense to have that that reflexive reference, but I think that is the exception. And in most other cases, it's probably preferable to leave it null. Okay, so Stringify is our toString function, which I'll say it again. Whenever you're creating new objects or new classes or whatever, you're going to want to help your future self in debugging whatever it is you're working on. And the best way that I've found to do that is to have a toString method for each of these objects, so you can see what's happening to the data, because that'll be your first clue that something is wrong. Something's wrong with the data. Okay, so again, we're using an interpolated string. I'm prefixing each one of these outputs with a bunch of tabs, so that well, I'll give you the example after I've done this. So it'll include all of the properties, basically. And then this is JavaScript notation for only do this second thing. Print out the value of whatever comes after or at the end of a series of AND operators, these ampersand notations. If this is not null and not undefined, basically if it has some valid reference in memory. And so it's really convenient whenever you're generating strings from data in JavaScript. Okay, and then this is a recursive call to the function we're defining right now. So that whenever you print out a node, you print out that node's subtree. So if you pass in the root node, or if you invoke this on the root node, then for the right child first, it'll print out the information. It'll increase the depth, which will increase the number of tabs that we have at the beginning. This is going to look awfully similar. So we verify that a left child is defined, has a valid non-null, non-undefined, non-falsy value. And then we invoke Stringify on the left child. Okay, so this, whenever we print it out, we'll have a bunch of nodes. And then whenever it prints out, the first one will have a depth of 0, so there will be 0 tabs. And it'll have some value. In the example we gave, the root node was 3. It'll have a height of 0, because its distance from the root node is 0. And then we'll recursively call it. So then the right child, I believe, when we left off, the value of the right child was 5. And its height was 1, because its distance from the root node is 1. And then it had null as a right child. And its left child, okay, so another recursive call. Left child was 4. It had a height of 2, and it was a leaf node, so both of these were null. Then it'll come in, it'll do the left one, same deal. The left child was 2, it had a height of 1, it had no right node, and its left child had a value of 1 for a height of 2, and it was a leaf node, right? So Stringify is doing this, and then that's what the recursive function calls will look like whenever it comes out. And so the tabs are just to make sure that whenever it prints out, it reads correctly. There may, I mean, it's always worth it to check to see if there's some built-in function that can do something similar. But I guess I tried long ago and I didn't find anything quickly enough. So I've developed a habit of kind of maintaining that on my own when I'm dealing with objects that are navigated recursively, like a tree, so forth. Okay. So that's what it'll look like when it comes out. And then we have one more function to define on our node object. So compute height. And we're doing this as a function because it's going to need to be updated periodically. So as we balance our tree, whenever we sort of juggle the nodes, we're going to have to recompute the height of the affected values of the affected vertices. So if there's a left child, then it's the value of the left child's height. And same thing if there's a right child. So these values are computing the height of the children, so we can compare. And if it's null, then it has just the minimum height. And so now we can make a comparison and compute the height of the current node as being oh, okay, yeah. So the height in this case, so it's the reverse of every context that we've used for height when discussing trees so far. So we're measuring now height from the leaf nodes. So how far removed is a particular node in a certain path from the bottom floor, basically. And so this is how we're going to measure imbalance. And the only way to do it is to make sure that now root, instead of having a height of 0, it is going to have a height equal to the longest path from leaf node to root in the tree. And the reason for this is so that we can compare imbalance whenever we're considering the distance from the bottom floor, basically, for these intermediate nodes. So whenever it's really imbalanced, then it'll show in the height comparison. Okay. It'll make more sense when we draw it out. But the +1 basically says, take the larger of my 2 children, and then that is my height. And then add 1 to that, and that's my height. And then we do it recursively up the line. Okay. So now we need to define our action methods. So when you're balancing an AVL tree, you have two actions. There's rotate left and rotate right. And then the way in which you use these tools is going to be how we keep the tree balanced. So if we have a tree like this, where there's some subtree located here, some subtree here, and then we have an x, y, and a z, where x is less than y, and z is also less than y, right? So we need to move this. So if given that it's imbalanced, or that we're trying to make it imbalanced so that we can in 2 steps make it a balanced tree, so in 2 steps instead of 1. But we need to preserve the property that everything to the left is less than, and so on. So the way we do that is we say we rotate left, so this moves to the left, this moves up and to the left, and then this one, well, z is already less than y, and and y is greater than x. So these two don't really have a particular comparison in that regard, in that they're both left-handed, so they both need to be in the left subtree. Okay? But we know that because z is in the right subtree of x, it's a descendant on the right line coming from x, that it's greater than x. So if we promote y up to this position and we rotate x down and to the left, then z, because y's left child is already taken, right? It can't still be y's left child. It has to replace x's right child. So before, z's parent, y, was x's child. Now y is the parent, and x inherits a new right child. Okay, and so if you went in the other direction, we would be rotating right, and we'll see that when we define rotate right. But those are the two options. You're going from something that looks like this to something that looks like this, and you're doing it by changing who has custody of z. Okay. Okay, so this, now that we have this image, and this is one way in which I like to use comments. So sometimes comments just point out obvious things, and over time you become familiar with enough with the code that you decide, well, a good function name is enough. And sometimes it draws you a little diagram. So because of this, it's kind of easier to know what we're manipulating instead of dealing with node.parent and node.right, to pull those out and just rename them at the beginning of the function, so that given this diagram, we have a parent node which is parent to x, right? So the parent of the node that's coming in. So we just hold on to that, because what sits here is going to change, so the parent is going to need to be notified of that. And then we pull out x and rename it. We pull out y and we rename it. And then provided y was not null, and if y is null, so consider what would happen if y is null. So we would have a tree with a null root. So each of these two nodes, these two subtrees, would now have a reference to a parent which is null if y is null. And so that can't happen. You would lose the connectedness of the tree if that happened. So we're going to throw an error if that's the case. And again, this is just stating our assumptions. We're assuming that that the operation is valid before we perform it. And if it's not, then whatever's calling rotate left needs to be aware of that. So this is a case where it's the right and proper thing to do to throw an exception rather than to invalidate the state of your data structure or the state of your data, period. Okay, so then now that we've guaranteed that we won't get an unexpected exception, except the one that we wanted, we can relabel z. Right? So now we know when we talk about x, y, z, which are normally terrible variable names, but because of the graph, it actually represents a very clear-cut concept, and so it's a little bit easier to discuss it in those terms. Okay, debug statement for us. Where we are, what the current state of the data is. The little trick that says if parent is not null, then print out the value. And then, and if it is null, then just print null. And then our variable names. So we want to see everything at the beginning of the function. Or I like to. You will develop your own style as you go forward. Okay, so x was the node that was passed in, right? So that's guaranteed to not be null. Or, I suppose if you don't trust that it's guaranteed to not be null, you could add a second one up here. Second check. That it can't be null. Or really, you would have to do it here. Because if we call node.parent, then we would get a null reference exception trying to access the parent property on a null object. But that's fine. we're not actually being tested on it, right? We're just demonstrating. But yeah, that's a place where I haven't included an exception, and it's debatable whether or not you need that additional check. But if you feel you need it, then add it and test for it if that's what you want. Okay. Z, and then I need to close. Okay. So then we update the values of x. So we replace its right child. And its right child at the end is going to be z. And we update its parent to be y, right? Because afterwards its parent becomes a y. Now we update y's values. So y has a new left child right here. Its right child was unchanged. Okay. And it gets a new parent. It's going to be what used to be x's parent. Okay, and so if z was not null, the only thing that changed for z was its parent. So in that case, we update it. Its new parent is x. And then the only thing left is to make the parent of x, the former parent of x, current parent of y, aware that the ward under its charge has been changed from orphan x to orphan y, or from child X to child Y. Okay. Okay, and so the complication is that we don't know, we're not told whether X is the left child or the right child of the parent. So first we check to see whether or not X was the root, right? And if it is not the root, right? If the parent is not null and it's not the root, then check to see here if it's the left child. If X, if the parent has a left child, and if said left child has a value which matches that of X, okay, then X was that child to the parent, in which case we've identified it and we can alert it that its new child is Y. And in the other case, check to see, again, making sure that it's not already root, and if its parent is and if it was not root, then it has a parent. So, and if we're in the else block, then check to see if it's the right child by first checking to see if there is a right child, and then compare. Okay. And so now, whoop. Okay, so now we want to recompute the height of X and its ancestors. And so again, remember that we're counting height now as height from the bottom of the tree. So Z would have a height of 0, X would have a height of the taller of these two plus 1, because the parent always has a taller height than its children. And then Y would have a height of the taller of these two plus 1. And so because height only affects the nodes on the top of the tree, or above wherever any modifications happened, then really we just need to start with Z and then work our way up all of its ancestors, because Z was the one that was juggled. And when we recursively compute it, everything that had whose height might have changed will have been recomputed if necessary. So, oh, sorry, yeah, Z's height did not change because it's at the bottom. So X is the first node whose height changed. X, and then Y, and then Y's parent, and so on and so forth. Okay, so we were passed in X and told to rotate, and then we get the result, and now we're going to return Y. And that'll allow us to make these cascading function calls if we care to. But it's not necessary. You could choose to not return a value from this, and that would be fine. But I think it makes more sense to return 1 in that case. Okay, so now we rotate right, and you'll observe that this is basically the exact reverse of what we had over here. So here it's unbalanced to the left, which is what we had after, and then the after was the before here. So these are inverse operations. If you called one and then called the other, then you would get the same result as if you hadn't called either. Okay, so very similar. Again, we want to relabel our nodes so that way have these easy to work with labels. So the parent node, we have our x, which is the root of the current subtree. We have our y, which is in this case the left child of the current subtree. Again, we want to make sure that y is not null. And then once we verify that, we want to label our z. Okay, so as before, once we've done our relabeling, then we update the parameter, the one that was passed in. Right? So we rotate that one. And when we do that, it's going to get a new left child. Right? And then it's going to get a new parent. And we update y. Y gets a new right child in x. And then it gets x's former parent. And now we conditionally update z. So if z is not null, then it gets a new parent, and that value is x. Again, we recompute the height. Again, we adjust the parent of y by making sure that it's not the new root of the tree, and then if that's the case, then we figure out whether it's the left or the right child of the one above, and then we update it as to the fact that it is replaced x. Other direction. Y. And so now we have balance, and balance has a little more intelligence. So these are the operations, the atomic operations that we'll use whenever we're correcting the tree. But balance is the function that we're going to call that has an awareness of the possible states that our tree can reach, in which case it needs to be balanced. So here, we're going to pass in a subtree root. So we know that we're always discussing a subtree. And we're balancing the subtree, and then we'll just recursively do that as we go up, and that should give us our balanced tree, our binary search tree. Just a second. Okay, so so the height of the left and right subtrees is going to dictate whether or not we have decided that we're too heavy on this side and that we need to rebalance by rotating right, or if we're too heavy on this side and we need to rebalance by rotating left. And so in order to get those comparisons, we have to pull those values at the beginning of the balance function. Okay. And then in this convention, null is given a height of -1 because a leaf node would have a height of 0 because it is 0 distance from being a leaf node. So this makes for easy comparison arithmetic because it's still an integer. And so there's 4 possible states that we can be in when we're unbalanced. So if the left height minus the right height is at least a difference of 2, then we have an unbalanced tree. And remember, it can still be balanced even if they're not equal, even if there's a difference of 1, because you can have a full binary tree, and then if you add one node, well, that new node is going to have, I mean, in this context, it'll have a height of 0, but it'll be on a different level of the tree than every other leaf node, but that's still balanced because it's the best you could do, just like filling in those valence shells. Okay, or valence orbitals, I should say. But we also have to consider grandchildren's heights in this, right? And so if this is the case, then now we need to know what the grandchildren look like. And so we're going to be considering the left child's left child and its right child by height. And again, all nodes have a height of -1. Okay, and then remember that we're returning the new subtree root as a result of this operation. So whenever y gets promoted, we return y. And so we're holding that reference here in subtree root. So going in, it was x, and now it's y. Okay, and so when it's broken, right, whenever this is the case and it's broken, in favor of left, then we go in and we see how it's broken. Right. So if the left, if it's broken and it's all the way stacked against the left edge, then we perform just a single rotate right operation. But, however, if that's not the case, and the left subtree is heavier than the right subtree here at the first level, and then we go down another level, and it turns out that the right subtree is heavier than the left subtree, or at least equal to it, then we have to make it even more unbalanced before we can balance it. Otherwise, we'll just end up toggling a node over and over again. So the way we make it more unbalanced, when left is already more heavier than the right side, when the left half is heavier than the right half, then we know we need to rotate right here. But in this case, where the imbalance is tending towards the middle of the tree, we have to first break it. So we rotate right. Sorry, we rotate left, I should say. And then we rotate right. Because we can really only truly fix it when it's the case that it's imbalanced and heavily biased to one of the extreme sides, and we'll see that that's the case whenever we're dealing with the rotate left operation. And then just to leave some notes to ourselves. And then this is just a reminder to myself that there's 4 combinations, right? So 2 variables, right? The first level and the second level, and then each of them with 2 possibilities, either left or right. So that's 2 times 2 possible states, and that's so 4 states overall. One of them is solved by a single rotate right. One of them is solved by a combination of rotate left and rotate right. One of them is solved by a single rotate left, and then the last scenario is solved by a rotate right, followed by a rotate left. Right? And so the final operation, right, depends on how heavy, like where the bias was. Right? If it was on the left side, if it was biased to the left, then we need to balance it by rotating right. So that final operation is indicated there. And then this happened, you get the necessity of executing 2 adjustments, 2 rotations. If you have either a heavy left subtree or a heavy right subtree, but it's all stacking up in the middle of the tree. So the first thing you have to do is break it by going against the immediate desire for balance at the higher level and making it even more imbalanced at the lower levels. And then that is easily rectified by the appropriate rotation at the top level. Right? Okay, so now we're going to do the chiral complement here. Now we're going to test to see if the right subtree is heavy. So as before, we're looking at the heights of the grandchildren, now that we know that we're going to be operating on the right subtree from that root node that was passed in. so in this case, if it's already imbalanced where everything is stacking up on the right, then we can fix it in just a single stroke. By rotating left. And if it's stacking up near the middle of the tree, then we have to break it. And then we can fix it. And now we call balance, passing it to parent. So this is access to the parent is the reason that we held on to the subtree reference, and the reason we updated it. I mean, we already had this variable, but if we wanted, we could have pulled out the parent up here. And then reference that down here. But, you know, there's all sorts of decisions like that you'll come across where, you know, there are many correct ways to do it. It's just preference. Okay, so now we have our means of maintaining the tree, of maintaining the binary search tree in terms of balancing it, but we need to define an insert operation as well so we can grow our tree, and insert will be aware of balance. So we're given a tree by its root, and then some value, and we wrap that in a node so we can have something that's compatible with our tree, and the value is the value property of that node. So whenever we insert it, we follow the rules of a binary search tree. And the general binary search tree is much more lax than the AVL one. So the AVL trees require a balanced tree, so that the height is as close to uniform across the tree as possible. But a typical binary search tree, it just makes left-right comparisons when it's adding a new node. So we're going to execute this loop until our newly created node has found a parent, has found someone to adopt it. comparison is pretty simple. We just have to see whether or not the current value is less than whatever node we're considering. And if it's less than, then, well, at each level we have a prospective parent. So if it's less than, then we need to see whether or not it has a vacancy available to be a left child. See if it's willing to adopt a left child. And if it does have that vacancy, then our new node has found its parent. And if there is no vacancy, then perhaps that parent's left child would like to adopt the current node. And you'll notice that this continue isn't strictly necessary, let me get it out of there, I guess, if we don't need it. Okay, and so now we do the same thing to the right. So if the value was greater than the current prospective parent's value, then we need to see whether or not that node has availability for a new right child. And if it doesn't, then we're going to have to try that right child to see if maybe that can be its parent. And if it does have vacancy, then again the adoption takes place. Okay, so once a parent has been assigned, I need to compute the height of the tree again for the new node and all of its descendants, or ancestors. And then once we have the height computed, then we can call balance. And we return the root because it's possible that the root of the tree will be updated on any given insert. So let's just take a moment to consider this here. So we're doing this so that as we store these numbers and as we grow our tree, then we store it in such a way that we have a preservation of ordering and this optimization in terms of lookup time. But you can see, following these very simple rules of just see whether or not it's greater than or less than the current node, how you can get a tree that looks more like a linked list than a tree. So if, for instance, we want ordering, so it seems like this should be compatible with an ordered collection of elements. So if we just added the numbers 1 through 5 in sorted order, what would that look like? Well, 1 was added first, so it's root. And then we compare, then we want to add 2. So 2 is greater than 1, so it goes here. 3 is greater than 2, so it goes here. 4 is greater than 1, greater than 2, greater than 3. Same deal with 5. And so in order to access 5, you have to traverse something that performs like a linked list. It has a number of operations in direct proportion to the number of elements stored just to find it. And so we want that faster lookup. So while the rules of a binary search tree are exceedingly easy to follow, creating the balance that allows you to get that lookup performance boost is the real trick, and that's why it's worth all of the effort that we put in. But this is how it gets unbalanced to begin with. Okay. Okay, so we've created a very small tree at this point. Just 3 elements, just to see what we have. So let's see. Okay, so it printed out exactly like we wanted. We can see whenever the rotate operation was performed. And so we could go through and we could perform the operations by hand, and then following all of this debug output, verify that the tree is doing exactly as we want. Or we can give it more work, something that's a little bit more complicated, and then use the output, the console output, at the end to make sure that the structure of the tree, using the tab indications in the left and right path structure, to rebuild the tree and make sure that the output holds, satisfies all of the properties that we want. After 3 nodes, it looks like it does. So 10 is between 5 and 12. And even though it was created second, it ended up becoming the root node, and everything, it's balanced and it's ordered, so that we have a binary search tree. So let's give it a few more, and make sure that it continues to stay balanced. Okay, so 10 is still the middle element. It has a height of 2, so its distance from a leaf node is 2. Its maximum distance. Right, so there. This has a height of 0, the left child, but its counterpart only has a height of 1. So the tree is balanced, even though there are more elements to the right. It satisfies the binary search property, and all of the imbalance is limited to just a single level, so that it really, even though it's not perfectly equal to the left and to the right in terms of the number of nodes on that subtree, there's no penalty as a result of it, because the height, the number of comparisons required to find a given node, is exactly the same as if you had something that was truly balanced in this scenario. So it appears as though we've done it, that we've created the binary search tree. Well, I mean, that was really all I had prepared for today. We have, let's see, we have 4 more lectures after today. Make sure that you see the homework assignment that I posted, and that's due next Thursday. And then I believe the final exam is on a Tuesday the 4th. That's perfect. Okay, so yeah, you're off the hook. Have a great weekend. Do your homework, and I will talk to you all next Tuesday.